Today we'll go through stress and strain measurement. The way you measure stress is using a strain measurement. So a strain gauge is used. A strain gauge measures strain, which is the change in length. The stress is estimated using the strain measurement using principle of solid mechanics. This is usually using Young's modulus. So what does the strain gauge look like? It looks something like this as shown here. It consists uh, of foil grid lines, as shown over here. And these grid lines are pasted on a backing material, which is usually plastic polyamide, which is insulator, so that way it doesn't conduct the electricity. So this thing is attached to the object on which you are going to try to measure the strain of. So this is the strain gauge, and it clearly needs to be insulated. And then there are these wire attachment points, as you can see here. So the way the strain gauge is attached is using epoxy or cyanoacrylate. The backing provides bonding and insulation, so that way, as I said, when you pass electricity through the strain gauge, it doesn't really conduct to the object on which you mount it. The way this works is, let's say that this specimen is bent or even loaded this way, then the strain gauge will bend, and that change in the bending of the strain gauge will induce a change in the resistance of the strain gauge, and you can measure the resistance as a change in voltage, which then is correlated with the strain measurement, and we'll talk about that calculation in just a minute. One thing to note is that strain gauges measure average strain. What I mean by average strain is it'll give you the strain about this point. It's not at a point, but it's about the area over which the strain gauge is attached. So that's considered as an average measurement, the measurement at a specific point. Okay, let's go through some theory before we um, see how to use strain gauge to measure strain. Consider a conductor of length L. Okay, it has a cross-section area of A. W is the width, H is the height. So the formula for resistance is rho times L divided by A, where rho is the resistivity, R is the resistance, L is the length, and A is the cross-section area. I take this equation and I take the differential of that equation. So delta R, delta resistivity, dL and dA. Then I divide throughout by R, which is sigma L divided by A, and I get a simplified expression which looks like this. Now what I'm going to do is I'm also going to take a differential of the area, because I will ultimately from that. A is width times height. If I take the differential of the area, I get HDW plus WDH. And if I divide it throughout by A, I get an equation which looks like this. Okay, so what I'm going to do is take this and plug this inside this equation and simplify. That's what I did next. It's a bit later on right here. Okay, so this is that expression, and I'll put that in a bit. So before we do that, let's develop some other things which we need to compute the strain. This is something which you learn in our first course in mechanics of solids. The change in length divided by the length is the longitudinal strain. So this is assuming that you're trying to apply a stress this way, and that will cause an elongation in the L direction. That's the strain which happens in the longitudinal direction. Now, what happens is when you stretch a material in the longitudinal direction, it actually shrinks in the other two directions. That is the transverse strain. Okay. So in this case, since there's W and H, there will be a transverse strain in the W and the H direction. So that is ET1 and ET2. And then there is this thing called Poisson's ratio, which gives you the ratio of the lateral transverse strain to the longitudinal strain. So that's for the two directions, W and H direction. So here I have a formula for, yes, it is a different color. So here is a formula for the change in W. So W was this, H was the height. So change in the width is Poisson's ratio times the change in lateral or longitudinal strain, and change in height is Poisson's ratio times the change in length. This is again using these expressions. Okay, now we come back to this formula, which I derived in the previous page, which is saying if you have A equals W times H, then you can take the differential and get a formula for the change in area as a function of change in width and change in height. So I'm just going to take this, write it back, write it again over here. And now based on this formula, this formula, I can get equation 4. So delta W divided by W is replaced here, and then choose. And let's say, okay, so this is subbed in here, delta H is subbed in here, and then we have delta A divided by A is now as a function of Poisson's ratio and strain. So this is how the area will change when the element is going to be stretched in the longitudinal direction. Okay, so this is just the area part. Now, I also had derived an expression for the change in R. Let's choose a different color for that. Okay, so this is the change in the resistance R. And the same expression has been rewritten here. Now, what I can do here is I can sub in the value of delta A divided by A. It's right here. So I just sub that in here. Okay, so you get this expression, and then we're almost towards the end. Now, what we can do is we can divide throughout by the strain and then get an expression for the change in resistance divided by the strain, and this you get this expression. It has the change in the resistivity, the Poisson's ratio, and it happens that this number, this entire thing, is actually defined as a gauge factor. It is a constant for the strain gauge. So once you create a strain gauge out of a certain material and you fix the length and fix the material, the gauge factor is fixed, and it's given by that. So if you look at a spec sheet for a strain gauge, you'll see that a line is called gauge factor, and that will be something like 2. It'll be of the order of 2 or something. So you just have to use that, but you should know that it comes from this expression. So now we have a formula for the strain as a function of change in the resistance, the original resistance, and the gauge factor. So we can rearrange this expression. So this, by the way, comes from here to get the strain, which is what we're after for a strain gauge, as a change of resistance divided by the gauge factor. So typically what you would see is R is typically 120 omega ohms, F is 2 gauge factor, and then those are pretty much standard values. So what remains here is to figure out or compute what delta R is, which is actually measured. And we'll get to measured part next. But once you have a measurement for the change in resistance of the strain gauge when the object is bent, you can then figure out what strain is. So the strain is really linearly related to the resistance. This is a good news because now we can use linear. All calculations happen to be linear. Okay, so this is a derivation for the strain as a function of change in resistance. Now let's get to the talking about determining this delta R. So again, recap, if you have the object is a strain gauge, you apply a stress, this strain gauge is going to bend because the object is bending, or in this case, sorry, it's stretching. Stretching is might be a better word, stretch. which causes a strain, which causes a change in resistance. And we somehow need to measure this resistance, because unless we have this resistance, we cannot find the strain. The strain we wrote down as delta R divided by. So we hopefully measure this. As I'll talk in this section, R is known, it's a constant, F is usually 2. And so we can find strain. So this part shows you how to compute delta R. The way this is done is using what is known as a Wheatstone bridge, the very standard circuit used in for such measurements. Okay, it consists of resistors, resistor 1, 2, 3, and the fourth one is actually a potentiometer. Potentiometer is a variable resistor, so you can change the resistance by turning a knob, and you've had one in your lab. Now this is connected to a voltage source, then there is some current flowing in the different branches. Let's assume I1 and I2 are the current flowing. There's a very specific reason why I assume that the current flowing in this voltmeter is 0. That's because I'm actually going to try to tune these resistances such that the voltmeter reads 0. And if it reads 0, then the current flowing through the branch AB is going to be 0. And so I'm sort of relying on that assumption when I draw these I1s and I2s. So first what is done is you put it in static balance mode, which is what you do is you have full control over the potentiometer R4. You keep turning it till the voltmeter reads 0. This should read 0. If that is true, then we know if the voltage here is 0. If the voltage is 0, then we know that the voltage at A is the same as voltage at B. Okay. So the voltage at A is same as that of B. And if this is Vs, then we can see that something like Vs minus Va is Vs minus Va is I1 R1, and Vs minus Vp is I2 R2. Is that right? Yeah. So this is basically telling you what is the voltage drop across Vs, S, and B. But if Va equals Vb, so this is if this is the same as Vb, sorry, Va, because the voltmeter is saying 0, then effectively this will become equal to that, which means I1 R1 will be equal to I2 R2, and that's what I wrote down here. I1 R1 equals I2 R2. That's one thing we need to know. We need this. The second thing is that we can actually compute what I1 and I2 is. I1 is the current flowing through this branch. So what you can do is Vs is here. This is 0 volts. So the voltage between Vs and 0 is, you can go this way. If you go that way, then you'll have I1 R1 plus I1 R4, and that's what I wrote here. I1 R1 plus I1 R4. So that's the voltage Vs. You could also travel this in the other direction, this way. In this case, Vs minus 0 is I2 R2 plus I2 R3. I2 R2, I2 R3. So this gives you another expression for I2. Okay, now we have I1, I2 from 2. We also have an expression for I1, R1, I2, R2 in 1. So we can eliminate. So from these two expressions, we eliminate I1 and I2 to get something which relates the ratios of the resistances. So R1 divided by R1 plus R4 is R2 divided by R2 plus R3. Now here we can do some math and show that it is same as R1 divided by R4 equal to R2 divided by R3. So all that's happening here is that this R1 is R2 times R4 divided by R3. And the reason why I wrote R1 in this fashion is because my strain gauge is actually going to be R1. That's the value of R1. So remember that this was adjusted, and this is how you get R1. Okay, so this is the first step. This is the static balance mode where you balance things out. Once you balance it, now we need to, this is when the object is not loaded, and this is the steady state resistance of the potentiometer and that of the strain gauge, no load condition. Okay, now let's assume that the strain gauge is loaded, so the resistance is going to change, and you can see that the pot has been removed. In reality, the pot is not removed, just that we will not change the potentiometer in this setup once it's been adjusted. We'll keep the R4 as it is from the previous step. Now in the dynamic balancing mode, the component is loaded. This causes the strain gauge to bend, or in this case, stretch. The resistance of the gauge changes. Clearly, if it is going to change in length, the resistance will change. And now what will happen is that the output voltage, yes, the output voltage is the voltage between A and B. So this is the difference in the voltage. So you can see that one end of this has gone to the positive of the op-amp, other one has gone to the negative one. And so V out is now, if you look at the, so V out will be V minus, but it'll basically give you that B is at a different potential from A, and so V out will be non-zero. So now what we can do is we can write similar expressions for, as I wrote down earlier, between Vs and Vb. So the voltage drop across the resistance R1 is going to be Vs minus Va equals I2 R2. And then Vs minus Vb is the voltage drop across the other resistor. I messed it up. So this is Vs minus Vb. So it's the blue one, and then the green one is on the left side. So here I've replaced R1 with R1 plus delta R because the resistance of the strain gauge has changed. Okay, so now from these two expressions, you can essentially subtract one from the other to get Va minus Vb. Effectively, I've eliminated Vs, and you get this expression. So V out is Va Vb. But Va minus Vb is this expression which I derived here. And so what I can do here is, well, I again wrote down a formula for I1, I2 based on the same reasoning as before. So I1 is the current flowing through the top branch, then Vs minus 0 will be the potential drop across the two resistors. And that's the formula here, and save for I2. So now what I can do is I can take this I1, submit it here. And I can sub in I2 in right here, and then I simplify to get a formula for V out. Okay. So V out is this giant thing. Note that all these resistances are known because, first of all, R2 and R3 were something which we intentionally put in the circuit. R4 we adjusted using a pot, so we know that. And then R1 is something we found earlier using static balance. So right here we computed R1. No R1, and what remains here is delta R1. So what we can do is we can rearrange that expression, and I did not go through the details, but you can rearrange this to show that delta R divided by R1 is this everything on the right. So here, as I said, all these things highlighted in yellow are known. R2, R3, R4, and R1. R1 was found from static balance. The V out is something which happens in this mode. It is measured. And so once you have V out and you have all these values, other values, you can then estimate delta R1. So this can be estimated because everything else is known. Once delta R is estimated, we can then compute what the strain is by using the strain gauge formula, which I derived some time back. So EL or strain is computed by delta R, which comes from this expression, R, which we know it's 120. In this case, actually, it's R1. It is whatever we got from the static balance, and F is a gauge factor, which is a constant for the gauge. So we have now developed an equation to solve for the strain based on the Wheatstone bridge and the resistances.